I'm ready to go. So I can see all you in the audience. Thank you. So the video's all running, ready to go? Okay, good. Wonderful. Now I can see all of you. So, if you start nodding off, I'm going to catch you at it. So our Acadia purple hoodie there in the front row, yeah, you. I can see you guys. So, and I've got audio too, so no snoring, please. I love that MacGyver analogy. That's great. I've never heard it presented that way. That's really neat. So just by a show of hands, just to get started, how many of you have telescopes and use them today? Just with your hands, if you would. Okay, there's some. So one of the challenges with giving a talk like this is what level to talk at. And again, I'm going to try and jump back and forth. There may be moments that I lose you. If you're not familiar with the topic, I hope you'll hang in there. You may find, my wife took me to a play last night, and I was literally asleep within about 30 seconds when it started. Fortunately, she didn't like it either, so we went home at halftime. But you may find this presentation doesn't capture your attention, and that's no problem. So, you can step outside. Those telescopes will be waiting you after the talk, and there's some spectacular things to see. So thanks for that great introduction. I'm going to talk for about 45 minutes. We'll have a Q&A afterwards. You can always Google me or email me, and I love the topic, and I love to answer questions. So please don't hesitate if you've got questions to ask them at the end or via email. I give talks all over the country, mostly by the web, sometimes in person. I was down, and I want to make sure people can hear me okay. Just nod your heads, yes? Okay, great, thanks. So I was in Florida at what's called the Winter Star Party, and they wanted me to give away a door prize because I'm an entrepreneur. I have this basement business, and I'm a cheapskate too, so I didn't want to give some, people are giving away these expensive telescopes. And I came up with this great idea. They make these eyepieces for telescopes that are very expensive. So I wanted to look like I was giving one, but I didn't want it to cost me any money. So this is what I came up with in Florida. I figured if somebody could grab it, they could have it. Now for New Jersey, I'm not sure what the animal should be. I don't know. Beaver? Raccoon? I grew up in Philadelphia, and I was the first rider on the Lindenwold subway line into Philly many years ago. That's my claim to fame. So let's get started. So how is it that we've managed to discover so much about the universe when we've barely set foot outside our front door? So this is a view from the Hubble telescope, and this is a piece of the sky. If you took a tennis ball and moved it 100 yards away, that's the piece of the sky that we're looking through. It's pretty crowded when you think about how small a piece that is. So images like these show the universe in 2 dimensions, which is a good starting place. And we can also get fleeting glimpses of a 3rd dimension when something crosses in front of something else. We're headed to Wyoming next summer for the total eclipse. I hope a lot of you will make that trek. Promises to have traffic jams galore wherever we go. A lot of the roads out here are 2-lane roads in the mountains. And with 10 or 50,000 people on those roads, it's going to be bedlam, really. So if we watch for a while, we can see a 4th dimension. And I'm going to go back and forth. There's 2 slides here that I'm going back and forth on. Can you see those stars down in the body going on and off at all? Okay, good. Some did. I'll keep doing that while I talk for a moment. These are stars that go on and off and pulsate over a matter of hours. They're called, this particular type of star, an RR Lyrae. So this is a time dimension that we observe, and there's some amazing things we can learn from stars by studying them that way. And if we spread out the colors, we get an as-if fifth dimension, which is a spectrum. It's the rainbow, and in this case, it has lots of gaps. And we're going to talk about that tonight. The thing is that about 80% of what we do and study and learn about the stars comes from studying spectra. It's remarkable. So whether you have a telescope or not, if you're an armchair observer or just an enthusiast interested, this is something that would be important to understand at least the basis of. Okay, so these spectra they're like a barcode, really. They're unique to every element and chemical composition. And you can see we've even named some of them on the sun here. You can see the sodium doublet. There's two bright lines on the bottom and the triplet up above in the green. So we're going to talk a little bit of history, a little bit of science, get that all out of the way, and then we'll get into the fun stuff and what you can do. So I've been an amateur astronomer for about 20 years. I'm a software guy. I'm a knuckle-dragging programmer. I break hardware. I like software, because of edit undo, or Control Z. Sometimes I wish that we had a Control Z in life. Wouldn't that be great? We could just go back to the beginning of the day or even further back and get a do-over. So I wanted to do some science with my telescope. I enjoyed looking at beautiful images I was capturing, but I wanted to do a little bit more. And so about 6 years ago, I got started, and it's become a passion of mine. But let's talk about the science for a bit. And first of all, of course, we've got our, one of the things I was just noticing, I'm using a little bit different hookup. You're going to hear me hitting my keyboard, I guess. You can hear that, right? Yeah, great. So you're going to hear me banging around, hitting keys and so forth. Anyway, so we go back, 100 years, 200 years, excuse me. The first significant observations were done here. They didn't really know what they were looking at. We can go back further in time, and of course, most of us have heard about Sir Isaac Newton splitting light. He did that with a prism, but you can also just bounce light off of a DVD or a finely ruled surface, or even pass it through a finely grooved piece of glass. We'll look at that in a few minutes. The sensitivity of the human eye varies. If you were to take a prism, and this is a fun experiment, take a prism and hang it in your kitchen or just shine it so the sunlight hits your white refrigerator, you'd see a rainbow just like this. And the distance we could see into the purple ultraviolet varies by age. Now, Mr. Arcadia up there in the front left with his young eyes, I'm not going to call on you and quiz you, so you can get that knot out of your stomach. I hate when people know about me in a lecture. So yeah, you can nod off. I won't bother you. I promise. I may pick on you, but I won't bother you. So now enough joking around. So Mr. Arcadia, he could see into an area that the rest of us who are older wouldn't be able to see into. It's pretty amazing because our eyes over time get less acute in certain colors. I had cataract surgery about 4 years ago, and I was all excited that I'd get to see more purple and blues. But the lenses that they replaced, the ones they put in, had filters in them, blue filters too, to protect my eye. So I didn't get the benefit from that. This is a painting of some white water lilies done by Monet, a very well-known impressionistic painter from the 1800s. These are white water lilies to our eyes, but to him they were blue because his lenses had actually been taken out of his eyes because they were defective. So if we go back in time even a little further, if we go back 500 million years, I'm sorry we're jumping around a little bit. This is a fossil from 500 million years ago. And Professor Parker saw this in the UK and he said, that looks like the surface of, a DVD or something finely ruled. And he hypothesized that there was a critter back then that maybe looked like this. So again, nature makes use of the same phenomena of splitting white light into its component colors. Now we come forward a little bit. A lot of us have heard of Bunsen and his Bunsen burner here. He invented the Bunsen burner to burn a sample and then split the light in a prism and observe the result. And in fact, the interesting fact is he decided not to patent the Bunsen burner. He decided that he'd make it available to man and womankind forever. We'd never see that in Silicon Valley today, but back then there was perhaps a little bit more of a sense of sharing. So down in the right-hand corner, you can see Kirchhoff, and he was a contemporary, and he formulated some rules to explain some of the things that were observed. We're not going to get into a lot of the details, but I wanted to show you over here is a rainbow that goes in the traditional colors, right? Roy G. Biv, as if somebody's name, red, orange, yellow, green, blue, indigo, violet. Notice that there's lots of gaps in that rainbow. There's a gap. And down in the lower right is another as if rainbow, but it's black just with a couple of lines. The difference is, and which one you get just depends on some of the physical, and I just went out of full screen with an extra escape key, depends on the physical nature of the object you're observing in intervening clouds. But the thing to notice here is that where there's an absorption line on the top in that reddish area, there's an emission line at the same place in the bottom one. So we'll look at examples of both these in a few minutes, but I wanted to show you those. So these are chemical fingerprints, and every element has its own particular unique fingerprint. Here's an example of it. In fact, I understand it's up on the wall there, this chart. You guys see it anywhere there? Oh, okay. This is a really cool chart. In fact, we created this and just started selling it for like 30 bucks. It's gorgeous for anybody who lives in the world of chemistry or physics or astronomy, because you can see very clearly that each element has its own characteristic spectrum. So when you talk about being a MacGyver, not only do you get, certain givens like light and gravity and magnetism, but you get certain tools. And all we got were these clumsy eyes and this, mediocre mind. And what startles me, it really does, is that with such raw and simple equipment, we've been able to observe such detailed and subtle nature of reality, of nature, really. And it's the first time I've said this. You can see it's a little ragged. Sometimes it's hard to wax poetic or wax fascinated, but it really does astound me. So this is just an example. Some of you may remember from physics class, a gas tube that you fire up. In fact, I've got one here. It's just like a neon gas tube or whatever, and you can see to the right there, it's going through a camera that we also manufacture for teachers. But you can see a spectrum, and then we plot the intensity over here, and we'll talk about that in a minute. Oh, there's a picture of that camera. This is an example of a lab that's being done at the University of North Texas. So a little more history, a little bit before Bunsen. This guy, Auguste Comte, said, we shall never be able to study the stars. They're too far away. And that was in 1835. But really, just a few decades later, all sorts of people were capturing the spectra of stars. How could have Mr. Comte been so wrong? Well, paradigms shift. We look at some of the medicine that was done 100 or 200 years ago, and we think how crude it was. And sometimes I wonder 100 years from now if we'll look back at the medicine we do now and go, oh my God, they were such brutes. They had no idea what they were doing. But I think the other reason Comte might have been wrong, he was a French philosopher, and how just wrong the French philosophers can be. So, I used that line when I was speaking to a club, and I didn't get a single smile. I got some smiles out of this group. And I got to thinking while I was talking, wondering, well, why didn't I get even a cracked grin? And then I realized I was talking to a club in Montreal. And so, open mouth, change feet. So how do these absorption and emission lines occur? Because it's all around us. When you look up at the stars tonight, you're going to see whitish or bluish, yellowish light. But if you put that light through a prism or something that splits it into its component colors, you would see what we're going to talk about tonight. So it's hidden in plain sight, but too small to see until we happen to get the right equipment and curiosity. You know, there's this model of the atom, the Bohr model, which we're familiar with from school, where the electrons are circling around a nucleus, and it's a good way to talk about things. It's apparently a little bit more complicated than that in reality, but for the purposes of discussion, here we see an example where an electron is jumping from the fifth shell to the second shell. And when it does that, when it falls, it releases energy, and sometimes that energy is going to be visible. And in this particular transition, it is. And you get a visible color. Here's a different transition from 3 to 2. You get a different color. And finally, just to complete the example, this one here, and this is a very common one. We use these Greek letters to label them. This is the hydrogen atom that we're looking at. And that hydrogen beta line, that aquamarine line, is a very well-known line. So this is how it happens. This is a photo of Niels Bohr. In fact, Katie, I want to ask you one question. How old are you, may I ask? 14, perfect, great age. So, you know, I bet your mother, who's sitting to your right, as I believe, maybe your father too, I bet if they're like my parents, and I think they probably are, they probably bug you sometimes about your posture. You know, sit up a little straighter, you know. I know, because my parents used to bug me. Don't worry now, you know, they can't turn and look at you, then they'd be rude to me. So look at our friend Einstein in this photograph now. Look at his posture, you know. He's like, what? I can't even mimic it. You know, it's something. So, you know, but the problem is Einstein won a Nobel Prize. So the deal is, get to work on that Nobel Prize. When you get that Nobel Prize, you'll be able to, when your parents complain about your posture, you just blow it off. So you got some work ahead of you, but go for it. Why not? It's a good goal to set. So here are some examples of some spectrographs, some professional spectrographs. And here's one down in Chile. You can see, again, down here are some people that are pretty small in relation to it. Here is one that was up on the Hubble, still is up on the Hubble, but we're not visiting it anymore. But this is when we were visiting it. And when the space shuttle was there, now see, my son, who's a little older than you are, my son says that box there that you see, that's actually the spectrograph. But my son, he says that it's a refrigerator and that it's filled with beer. And he assures me that when the cameras were off on the shuttle, they were real party animals, and that was just part of their partying. And I can't prove him wrong. So now here's a device that's again used by an amateur. It looks pretty complicated and pretty expensive. And what I really like is this gas tube that's just, look at that. It's just sort of jammed in there. It's got 2 little pin heads on the end, you know, and little pins. And I just pictured Dale with these little alligator clips, clipping them on, you know, and drawing a spark, ruining his night vision. But the reason I wanted to show you this is to show you, again, what it doesn't have to be to do the kinds of observing that I'm going to talk about tonight. This is a $200 grating. It's actually like a prism. It splits the light. I can't quite get you a rainbow there. There's some greens. It's called a star analyzer. And when you screw this onto your camera, you get as if a prism split light. And what's amazing to me is what comes out of that light, the kinds of things we've just been looking at. So here's an example. In fact, I've got a DSLR here just to show you that, again, we just have this little thread adapter threaded on here, and then there's the grating itself just screwed on. And then you just mount this on a telescope. For those of you who do this kind of thing, this is something new to me, so this particular piece of equipment, I just recently got what's called a cold shoe that slides onto the flash attachment, because I was having a heck of a time pointing this, and there's nothing like a green laser to help you point at stars when you're out in the dark. It's really remarkably bright. So just with a DSLR and no tracking, if you orient everything right, you look down there, you've got a rainbow, and there's an absorption line. That's actually that hydrogen beta line we looked at a minute ago. So this isn't hard to do. It's not hard to capture. It's not hard to understand. So here's an example of our grading on some cameras. Actually, I didn't intend to bring it out, but just to give you some diversion, here is that one on the upper left. This is a imaging source camera. I really like the one on the right there. And anybody who uses a hose clamp as part of his scientific equipment, that's my kind of guy. There, down on the lower left, you can see another example of the camera. Any CCD. Doesn't have to be a color camera. Doesn't matter. So there are higher resolution devices also, $800, $4,000. But most of us start with this $200 device because it's so inexpensive. This is the kind of thing, actually, that people do for high school science projects. And we coach people on that. Usually they buddy up with a local astronomer. And it's a big science fair hit because there's so little astronomy and astrophysics done these days. There's so much biology done in science fairs. So here's an example of a telescope where we've got the high-priced device and also a DSLR piggybacked on the telescope. Okay, so now we're done with all that stuff, the history, theory, equipment. What can we actually do? Let's take a look. So we got our starlight coming in, right? And we put the light through one of these gratings that I'm showing you here, and you get a spectrum, right? Some of the starlight goes straight through, and some of it gets bent off. So here's an example of that. Now, each of these is a different photograph or image we took of a different star. And you can see, because you're familiar now with spectra and know that these gaps are absorption features, but notice how they differ. In fact, let's just look at this just for a second. We won't study it. It's too late at night to study anything. So if you look carefully, you can see that this gap is really much stronger than that gap or that gap. Why would that be? Well, these stars are listed in temperature order on the left in what's called, the acronym is Oh Be a Fine Girl or Oh Be a Fine Guy, let's be fair here, Oh Be a Fine Girl, Kiss Me. It's just a scientific nomenclature for temperatures of stars. So the hot stars are at the top, but notice this star here, it's a type A star. It has the strongest absorption line. And that's because, remember, these gaps in the spectrum are happening because electrons are jumping up and down. They're basically getting energized by the heat from the sun or the star, and then they fall back down again shortly thereafter. Well, these stars at the top are too hot. And some of the electrons, they don't just jump up to a higher shell. They jump and they're gone. And some of these stars down here that are cooler than that type A star, not all the electrons get pumped up to the highest level that has to occur in order to get this hydrogen beta feature at like 4,800. The measure is angstroms. That's just a color measure. So, and then look at these cool, for those of you who are familiar with the stars, these cool type M stars. Notice there's really no hydrogen alpha or beta there, but look at these bands over here that these stars above don't have. See, so we're starting to see differences. And this is what really stimulated the thinking 150, 100 years ago. What's different amongst these stars? And these cool stars are so cool that even though they don't have any hydrogen electrons jumping around, they've got some complex molecules that are able to survive on the surface without being destroyed by the intense heat. So we're already doing science. So, but let's go a step further. I want to know, on your projector there, can you see in that crosshairs that it's a little bit dimmer? Shake your head, yes or no. Can you see there's a little just inside that crosshair? Yes? Okay. See, and that's great. You can see it there. So you've got a good projector. But to do science, we have to do a little more than just sort of go, you see that gap? So what we do with science is we plot the data. And we do that, if we go in the right direction in our show, we do that by, and this is the only sort of math we're going to do, is we plot the intensity of the light that we're seeing. So this really bright star here shows up as a really strong peak. And this generally bright area shows up at that broad area. And notice we also, if we can get my mouse to work, sorry, I jumped out of full screen again, just a moment. There we go. Is that gap I pointed to you shows up in that graph. So now we're doing science, right? Now we can say to somebody, how deep is your dip? What percent of the total height is that? How wide is that gap? How far over is that gap from the star? What color is it? So all of this can be done by plotting the data. So how do we get that plot? And that's where we use software. So what happened with me is I went out with a grating one night at midnight with my C8 telescope. Maybe there'll be one out there tonight when you go out. I came in at midnight. I had grass stains on my knees because I was looking at Vega. And the next morning, I tried to use some of the freeware that was out there to process this data. And I really, after about a half a day, I gave up. I said, this is so frustrating. The software is so shabby. That's what I do in my day job is I develop software. This is a hobby. I want to have fun. I don't want to be angry at the software I'm running and the author. So I gave up. But weeks later, I decided, I really want to do science. So I ended up writing a piece of software, and I want to show it to you because I think it will help you understand just how easy this all is to do. So let me just pop that up for a second. Give it a second to pop onto your screen. Now, can you see the whole screen now? Okay, give it a moment. It can take a moment. Oh, maybe just one little thing is showing. Let's get out of that, just that little adjust thing. Let me try sharing again. Give me just a moment. Let's see what else we got here. There we go. See if that does it. Well, that didn't do anything. Okay, I tell you what I'm going to do. I'm just going to share my whole desktop. You're going to see everything. There. Let's give me just a second. This is so amateurish of me, isn't it? Not to have this all set. Jeez. So you can see my desktop now? Oh, you can see RSpec now. You see the whole program? Oh, okay, let's do that. Okay. Look, I'm blushing. I'm embarrassed. Such a rookie move not to be able to put the thing together. Talk about colors. Okay. So on the left is a video that I made that first night out. And I wanted to just move it to this spot to show you. This was actually what I saw when I looked through the eyepiece. And it's also what happened, what my camera recorded. And you can see there's the star and there's the spectrum. And we can't quite see that gap we're looking for. Now, the first mistake I had made was I didn't screw this on exactly straight onto my telescope. So I'm going to start this video playback. It's not going to stay color for long. But then I'm just going to rotate that image around. So we had to put this into the software. See, I say we, so it sounds like I'm a real company. It's just me. So I'm going to rotate it around to its horizontal. Look, it's moving around because I kicked the tripod. I told you, I'm a software guy. Let's rewind this video. And now I just bracketed it in. So now what's happening over here is the software is plotting the light intensity between these orange lines over here. So that peak is the star. And this broad peak is that data. And right there, coming and going where my mouse is, you can see a couple gaps, and that's these dips right here. So now this is jumping around because of what's called seeing, right? You know how when you look at something like over a hot car hood, it wavers and flickers? Well, stars do that too. That's what makes them twinkle. So this is twinkling, basically, to use the technical term. So one of the things we can do in the software is I'm going to ask the software to average consecutive frames. And this is the average. So all that noise disappears. And for those of you who do imaging, it's sort of cool to see this. I'm going to pause the video, and we're just going to spend another moment here. But I want you to, again, appreciate what we've just done. We've just screwed a grating onto our camera. We have an image, and by plotting the intensities, we're now seeing the spectroscopic features. Now, there is a calibration step which takes about 20 seconds that I'm going to skip. This last step I want to show you is I'm going to say to the software, show me where the hydrogen absorption features should be. And here we can see the software saying there should be a dip right here. Well, there is. There should be a dip right here. Well, there sort of is. Looks like I didn't calibrate it that well. So there's dips right where we expect them. So we've now calibrated, and now we're able to say, well, there's hydrogen on this star. And we can say other interesting things about it as a result of this. It's remarkable how easy it is. I didn't have to do anything, really. I just dragged these orange lines around after I rotated it. So I want you to remember this. This is Vega on an 8-inch telescope. Remember this because we're going to see this image in a little bit again. And the other thing I want to show you, just because I'm easily amused, hopefully you are too, is there's a dip. That's a hydrogen dip. I'm going to turn off that stacking or averaging and just play the video. Now, can you see? You can sort of see there's a dip coming and going there in the noise, right? But our eyes aren't really good at integrating and filtering and averaging. Now, what I like to do is when I turn the averaging on, watch how that dip slowly appears as all that noise gets averaged away. I don't, for some reason, I get a kick out of that. All right, let's stop the playback. Again, remember this view of Vega with a couple dips, and we're going to go back to our show, which is here. So let's give it a chance to show up on your screen. So you guys can see the screen capture now? Thanks, Jim. So let's look at what you can do with a small telescope and a grating in the software. Here's our first example, and that's just, there are some stars, you know, and you can see they all have different spectra. For example, find my mouse here. This star here has some peaks in it, which says it's a different type of star. There's the source star. This star has some dips in it. This has some dips. So that's what the full sky looks like. Let's look at a particular star. It's called a Wolf-Rayet star. Now, I have to make a confession here. When Janet sent me this, I couldn't remember what a Wolf-Rayet star was. You know, this stuff goes in one ear and out the other. But not all stars are the same. So I had to look it up. You know, Wikipedia is your friend and my friend too. And so a Wolf-Rayet star is an older star that it's blown off some of its gaseous shell, and we're actually able to see down towards the core. So Janet, with a DSLR, took a spectrum of this star and saw some very bright peaks. And she was able to identify those as carbon. See, as a star burns, it starts burning hydrogen and then helium. It burns successive elements, and one of them is carbon. So, you know, so we're looking at more or less soot, the results of that burning. It's pretty amazing that we can see this in just 30-second exposure with the DSLR. So let's look at another one of our favorite objects, M57. It's not all that interesting. It's got a couple of pieces of data, but see this, just one other technical thing about the technology. Most expensive professional gratings have a slit, tiny little slit, so that they can just look at a piece of what they're looking at. And one of the reasons this is so inexpensive is it doesn't have a slit. So what you do is you see the whole object. So in this object in particular is just made up of two gases. So we can see the spectrum of those two, hydrogen and ionized oxygen. That's what that Roman numeral 3 next to the oxygen says. But let's look at another object that's well known to us, M42. So I don't know what time. Is M42 going to be up tonight, or it comes up pretty late for you guys, doesn't it? For all of us at this time of year. So you'll have to come back this winter and look at M42 through the telescopes. This is done with a slit spectroscope, so the peaks are a lot sharper. But again, there's the ionized oxygen. These are the components of this object. It looks like a cloud, doesn't it? Well, you know, for those of you who have telescopes and have observed before, I want you to remember the first time that you saw M42, which is called the Orion Nebula. For me, it was at a star party, much like the star observing you're going to do tonight after my talk. I was all excited. You know, there were telescopes that looked like those circus cannons that they shoot people out of. You know, it was amazing. Everybody was excited. When I got up to the telescope, I have to tell you, I don't want to take any wind out of the sails tonight, but I was really disappointed. It was a smudge. It wasn't colorful. It just looked like a smudge mark on the eyepiece. And tonight you'll see some more interesting things than that, I assure you. There's other things to look at. But you know, no matter how it is that you first saw M42, my bet is that you still come back and look at it. And so do I. And why would I if it was so boring that first night? Because Now when I come back, I understand what I'm seeing. So I bring that understanding to my eyes. This is a birthplace of stars. It's a stellar nursery. Gases are collapsing, coalescing, heating up from gravity, and finally igniting into a blazing star of light. And knowing that, this becomes more interesting to look at. So for some of us, we may not want to do a lot of science with the spectroscopy, but it brings an added appreciation. So real quickly here, we're going to run through some examples. This is Uranus and Neptune. And again, you can see that, my cursor is black and so is the background. So it's hard to bracket in things. But there's the spectrum and there's the plots from the software. Deep, deep dips. That's from the methane. Now I have a quick adolescent story told by an adolescent. And that is, there's a big conference up just at the northern border of New Jersey and New York every spring. And in 2010, I went out to show my new software and this grading. And my wife was with me. And they made a videotape of me being interviewed by a big guy at Sky and Telescope. It was great. My wife said, Tom, she was there with me. She said, Tom, if you're going to talk about Uranus, make sure you pronounce it Uranus. You don't want to be talking about methane gas and pronounce it differently. And if you look at that video, you'll see, as I did just now, as I'm walking up to talking about Uranus, I'm like, my wheels are spinning a little bit. My eyes are a little bit unfocused because I'm like trying to rehearse. How do I say it? How do I say it? But anyway, it is remarkable that we can look at this kind of thing. This is done with just a 8-inch telescope and a video camera, as was that really colorful image I showed you earlier. So now this is Albireo, and you will probably get to see this star, this double star tonight. I hope you will. And if they defocus it a little bit, you'll be able to see that the stars are two different colors. And when we graph the spectra we get off of them, yeah, there are gaps, but that's not what we're talking about here. Right now, what we're talking about is the fact that this one is so much stronger over in the yellow, and the other star is so much stronger in the blue. That tells us something about the temperature, right? Think about, for example, a candle. What is the hottest flame in a candle? Is it the yellow or the blue? It's the blue. So temperature and color are closely related. Let's see, what's next? Get my mouse to work here. There we go. So while we're reading that, I wanted to just make sure I was properly attired. There's the hydrogen absorption line right there. So Henry Draper, back in 1881, saw the spectrum of a comet. I figure if Hank can do it, we should be able to do it. So here it is. Again, we're using a DSLR. This is, when I say we, this is done by Robin Leadbeater, who's designed this. And you can see a comet there. Now, and some of the chemicals that we were able to identify on the comet. So as I mentioned earlier, because this doesn't have a slit, it's tough to look at extended objects. But this comet was compact enough that we could still get a spectrum off of it. So in just a little bit of the science, this is just from a few years ago. The belief is, although it's changed somewhat recently, is that these comets brought a lot of the building blocks of life, including water, to the Earth. So it's sort of fun that we can study them in our telescopes. Here's a comet from a few years ago done just with a really small telescope and a Canon camera, and we can see the carbon. Those are called the swan bands, as it turns out. These are hot. So the swan bands of the comet are visible there. Okay, so now this is sort of cool. Again, anybody who uses a C-clamp on their telescope equipment, my kind of guy. You can see the star analyzer on the nose piece of that camera. This is a meteor. The meteor is moving from bottom to top, and right here there was a bolide, or a sudden brightening. And you can see some of the minerals we were able to observe. So again, this is the same plot that we saw in my software. It's just an intensity plot of the rainbow that we captured. And this is an interesting story. So remember, we were talking about Bunsen in about 1850. He discovered that he could split light, and he was studying all the different elements. He was burning everything. He was like a teenage pyromaniac. So he he had categorized, he classified everything he burnt and where the colors were, where he would see spectra or peaks. So a few years later, right around the time of the Civil War, 1865. Now, when I talk to clubs in the South, I have to talk about that being, the War of Northern Aggression, but same war. So right around then, there was a total eclipse. And at the moment, just before the eclipse is total, the sun becomes a tiny little sliver. And then, even though we don't have a slit, we can study the spectrum. And this is what we found. All sorts of emission lines. And when they compared these emission lines to what Bunsen said he had found burning things, we found a match. So, this line, Bunsen burnt some hydrogen and found. This line, he burnt something else. So we said, oh, great. But there was one line that he had never seen before. We didn't know what it was. So what they did was they said, we don't know what it is, but we're scientists. We know the wavelength is about 5,900 angstroms. It's sort of yellow. And let's give it a name so we can talk about it. In Greek, the name for sun is Helios. They called it helium. We had never handled helium before. We were observing the physical properties of something on the sun 93 million miles away. We didn't know what it was. Now you fast forward about 40 years. Two guys were studying the gases that came off of uranium when they heated it. It's a tough job. I think their kids had about 3 arms. But when they studied that, they discovered that that gas had an emission feature at the same place that we saw an emission feature on the sun. And they were able to say, Eureka, we just found helium on the sun. So this is the kind of thing that we can do as amateurs. There's rare chances to do it. Of course, there's one coming up next summer. But there's other ways. If you have a slit spectroscope, you can do it all year round. So you can also, if you're into it, you can study the spectra of novae, suddenly brightening stars. Okay, a couple more examples, and we'll call it an evening. I want to remind you that what Doppler shift is, if you're not familiar with it, and that is just when something is coming towards you, its pitch gets higher. And when it's going away from you, it gets lower. So traditionally, although there aren't many these days, when a train comes through a station with its whistle going, it goes, right? High, low. Well, the same thing happens with light. You can hear that, by the way. You don't need a train. Just open the window in your car on the way home tonight and listen to the cars going by. You'll hear shoo, shoo, high, low. So you're hearing it higher pitch as it comes towards you and lower pitch as it moves away from you. So the same thing happens with starlight. So we might be expecting from Bunsen's records to find some absorption features here, but they show up to the right, sort of to the right. There we go, to the right. Or they might show up to the left, depending on whether what we're looking at is going towards or away from us. Let's see what is done with that by amateurs. So here is a galaxy several years ago, and you can see that star in the middle there. That is a supernova, if I can bracket it in there, that for a short while was brighter than the billions of stars in its galaxy as it blew itself apart. There it is. And that's what it sort of looked like. This is a different one, but it was, blowing up, basically. So there's the spectrum, and there's the graph. Now, the interesting thing here is, before we look at the graph, is to see that David Strange captured that with a 9-inch telescope, our grating, and just 15 minutes worth of, exposures. So, and what he found was a very strong dip right there at about 6,000. Now, scientists had already established that absorption feature, that gap in the spectrum, is the way that we can identify a particular type of supernova blowing up. That's ionized silicon. It's silicon blowing up. And David measured that on the x-axis there at 6150. So now look what we can do with that number. So there's the number that David observed on his graph. If I can find my mouse here, there. And there's what Bunsen would have measured it as if he had burnt some beach sand in his lab. If we take those two numbers and put them into the Doppler shift formula, Wikipedia is my friend again, I couldn't remember what it was. do a little bit of math. We have now calculated how much blue shifted that light is because the shell of that supernova is coming at us crazy fast, to use the technical term. 22 million miles per hour. So there should be two wows there on this slide. One for wow, that's fast, and one for wow, I can't believe I was able to detect that with just a 9-inch telescope in less than 15 minutes. We're seeing the Doppler shift of that shell as it races towards us so fast. So here's Adam Rees, who won the Nobel Prize a few years ago for studying supernovas. And he was the one in the late former century who really discovered the cosmological expansion, that we were steadily accelerating as a universe. And he used these supernovas to do it. He looked at how much shifting there was going on. And I think he probably used a piece of equipment a little more sophisticated than this, he and his team. But we'll talk about him if we have him in a few moments. So here's an example from Sky and Telescope of somebody who did the same kind of thing. When the star's at rest, you'd see that dip right there. But one day after the supernova this guy was observing, the dip was way to the left because of this blue shift as the shell comes towards us. And then you can see over successive days, at 4 days, at 26 days, that dip is moving back towards the normal unshifted dip. Okay, so I want to show you another cool example. For those of you who aren't familiar with the kinds of objects we amateurs look at, one of them is called a quasar, quasi-stellar object. And I'll let some of the attendees who are amateurs tonight go to their iPhones and quickly look up what a quasar is, because I can't remember. So a quasar is a really bright galaxy in, basically on its way or having become a black hole. And we've got one in this photo here. It's the brightest one that exists, and it just looks like a dot there. And there's its spectrum. Let's zoom in on its spectrum. There it is. Again, it just looks like a blur. But there are two dots there, two brighter spots in the spectrum. Now, again, these would be colorful if we had a color camera, but black and white is a little bit more sensitive, so that's what we use. And when we plot it, we get that curve with a couple of really strong peaks. Now, this guy, who was 12 or 13 years older than my Mr. Acadia there, he was in his mid-20s, looked at this graph, Martin Schmidt, and he pulled his hair out because he couldn't figure out what this was. And he said, well, let me just prove that it's not hydrogen. And he looked at the hydrogen curve, and you'll remember that's the one from my software I asked you to keep in mind. And he was stunned because he found out that those peaks were the same distance apart as on a local star, but they were shifted way over to the red, which meant this object was moving away from us at an astonishingly fast speed to get that much redshift. And this is the kind of thing that amateurs can do with, this is done with a 9-inch telescope and a modified security camera. So these things are possible for us lay people. Now, what amazes me is that this light 2 billion years ago left that quasar. It's 2 billion light years away. And it still has that information. That the light can continue to carry that information over such a long period of time is fascinating. Human beings, not so much. Here's Martin Schmidt a few years ago. So things we all change in remarkable ways, mostly good for a while. So far we've been looking at features like that. These are the hydrogen features that we're looking at. And they're about 50 angstroms across. That's the smallest that we can see with these inexpensive devices. If you want to look at the detail, suppose you want to look at, we want to zoom in on that dip. Let's do that. There's a zoom on that dip, but this is with one of those expensive spectrometers. And they say a friend of mine lived in LA for years, and he was a mechanic on Porsches. He went on to work at Microsoft. And on the showroom wall, you may think, what is he talking about? I came here for astronomy. On the showroom wall of that Porsche high-end sports car showroom was a sign which, believe it or not, applies not only to cars, but also astronomy and so many other things. And that is, speed costs money. How fast do you want to go? That's really what it comes down to, right? So there are some limits, obviously, but these higher end devices do take a little bit more money. Okay, we've got to finish up quickly here. I want to show you one other example, and then we'll just finish up. This is a rotating star, and this edge here is, let's rotate it this way, this and get it centered. This edge here is going away from you, right? And this edge here is coming towards you. So you have Doppler shift in two different directions, towards you and away from you, because it's rotating. That smears out the spectrum. And so rather than this nice tight absorption feature that you see on a star named Vega, you get a collapsed sort of smeared dip. This is done with a slit spectrometer, but it gives you an idea. You go, how can a scientist possibly know how fast a star is spinning when it's that far away? It's not that hard once you understand what it's all about. Now, you know, I have to confess as we finish up here that I forgot to bring something here to my presentation desk. So I'm going to reveal something. My wife has asked me never to do this. And that is that it's really not exactly the professional studio look that you might expect. So this is my man cave. Let me run and get what I need. I'll be back in just a second. I promise you I'm not going far, but what I'm doing is just grabbing a sky and telescope off of a stack. Let's get this back up. Much better. Now it feels much more professional again. So what I wanted to show you in this is, you know, for those of you who read these, in the back, they have these gorgeous image collections that amateurs have taken. And I never grab the same sky and telescope. I never rehearse it because I'm always looking, you know, I never have any trouble finding what I'm looking for. Let's see if I can find one here. Yeah, here we go. Look at this beautiful image there. I mean, that's the kind of stuff that we dream of capturing, but then you read the fine print. And this is by Larry Van Vliet. This is 25 hours of photographing time, of integration. 25 hours. You know, I live in Seattle. I don't get that much clear sky in an entire summer sometimes. And furthermore, I don't have the skill, the telescope, the dark skies, the interest, the time to do that kind of thing. I'm glad Larry did, because those are just gorgeous images, of course. The reason I bring that up is because what I'm showing you isn't that. This doesn't take a lot of skill. It's the kind of thing anybody can do, which is, you know, it's really been very nourishing for me to learn how to do it, because I always thought that this would be hard to do. So it looks like I can't play that this is an animation. It doesn't look like it's playing right now, so we'll move on from that. And let's just talk about how you get started real quickly here. You get one of these gratings for almost $200. You need any sort of camera that you've got, DSLR, astronomy camera, whatever. You might need an adapter, and you need software. This is that free software that I mentioned that I started with. You can download it and try it out. This is my software, RSpec. See, I'm not a very good marketer. That's the first time, perhaps, that I've said that word, RSpec. I'm supposed to be hammering it into your brain, you know, every slide till you're ready to shoot me. So it was a hot product in Sky and Telescope in 2012. We're going to skip those. Again, there's a variety of books out there. For those of you like me who tried learning things, you know, in the last century, it was very frustrating. These days, things get a lot easier because there's a lot of publications on the web. There's people to answer questions, including me. There are opportunities to do collaboration between professionals, the American Astrophysics Society. Some of the names down here are amateurs. Some of you may recognize Christian Buil, who pioneered CCD imaging in the 1990s. So we've come a long ways from on the left. That's this, oh, there it even says his name. That's Fraunhofer, one of those early people 2 centuries ago who said, gee, there's pretty colors after we pass the sunlight through a spectrum. This, of course, was Bunsen's buddy who talked about some of the rules and principles of what was being observed. It's a long way, and to me, it's a grand and magnificent discovery that is, as MacGyvers, humanity were MacGyvers just trying to tease out some rules and properties that can make life better. You know, all of us in this room and me, we were born so lucky in our lives. And a lot of that, of course, is the relative peace in which we've lived, but as well as the technology and science that have blessed our lives. You know, the next time you look down at your arm and you see that vaccination, I've never done this particular riff before, but it's a big one. And you see that vaccination on your arm, that little scar, think about the significance of that. Think of the countless hundreds and thousands of generations of humans, if you think they've gone back thousands, they probably have, who lived and died of diseases that we were inoculated against when we were young. It's really remarkable. And astronomy has contributed to those discoveries in countless ways, in enormous ways. And as amateurs, for those of you who don't do this, as amateurs, we seek to share a little bit of that glory, just sort of look on and reproduce some of the observations that people make, and just admire just how grandiose and magnificent the creation is, and how remarkable it is that with this meager mind, as MacGyvers, we've managed to tease out information that comes to us across billions of light years and from stars that are impossibly distant to us. So thank you so much for attending my talk. I appreciate it. I'm, again, delighted to have the opportunity to speak with you. Most of you stuck in there, and I know maybe it wasn't as interesting as you perhaps had hoped. But again, thank you so much, and have a great evening outside tonight. You're welcome. Great. That's a good question. I don't know. I've got my little periodic table here I was looking at earlier. I don't think so. I think most of the elements that we find are, the very low elements. In fact, the one other thing to share, and that is, it's like the first dozen or so elements. I mean, there was just hydrogen and helium in the beginning. Everything else, including that jacket that you're wearing and the paint on the ceiling and the dirt outside, didn't exist until one of these supernovas blew up and synthesized all those higher elements. So I don't know. I'm sort of a one-trick pony. It's a really good question, but I suspect not. And I suspect they would be so small in terms of their abundance that we might not be able to detect them. It's a good question, though. Other questions? Good question. It's all up to your camera, and the grading isn't particularly good at IR. Infrared is sort of reddish colors. You can take the infrared filter out of some DSLRs, and some CCDs are more sensitive in red, but you can do it in the infrared, not particularly effectively. And the good news is there's plenty to see in the visual light range, so IR isn't as important. IR also is sensitive to water in the air, which is one of the reasons they put observatories up on mountains. So unfortunately here at our sea level observing, there's a lot of water in the air to interfere. That's a good question too. Anything else? That are unknown to us? I don't know. I don't think so. I'm embarrassed. You guys are asking me good questions. I'm a one-trick pony. It's a good trick, but I don't know. I don't think so. I think most of them, it was just around the time of the turn of the century, between the 18 and 1900s, all this was happening. And I don't think there was anything discovered spectroscopically, partly because the stars typically it's tough to discern what's what. When you look at the spectrum of the sun, you may remember that one of those first slides I showed, I'm going to try and get to it. You can hear me hammering on my keyboard. There's a lot of lines there. And in fact, there are more lines in the sun when you look at it in a higher end device. And it's hard to figure out what's what, because sometimes the lines are so close to one another. You go, well, maybe that's this or maybe that's that. So the upshot is I'm just trying to distract you. I don't know the answer to your question. Sure. Good question. So what was the second part of that, Jim? It is like a prism, but it's not a prism. But it does the same thing. A prism has a couple of faces, and we bounce the light around in it, and as a result of that, the different lights get bent different amounts. And what this grating is it's a it's a piece of glass, very fine lines grooved in it. And so it's a diffraction grating, if you've encountered that term perhaps before, that bends the starlight by color. So it's like a sieve, or it just routes the light so that the red gets bent different amount than the blue, than the yellow, and so forth. So it's just, I mean, literally, if you hold this up to a ceiling light, you'll see the whole rainbow coming off that ceiling light, just like it was a prism. Thanks for asking that. That's a good question. Not only is it a good question, but I knew how to answer it, so I'm particularly gratified. Other questions? Okay, well, you know where to reach me. Thanks so much, everybody. My pleasure. Have a great night. Go out there and do the fun stuff. Observe. And ask them to show you that double star that has 2 colors. Anyway, good night. Thanks again. Bye. Bye. See ya.